And for those who now in the classroom, I would like to invite you to turn on your camera if you feel comfortable. It will be helpful for me instead of looking at the black screen to see someone there. Thank you, thank you. And let's get started. First, let's do some reviews on what we learned in last class, and then we are going to learn some new things today. Just a friendly reminder, after this class, the recording of the class is going to be posted on Canvas, and also the homework will be posted as well. And that is still 1 week from now. And next Monday, we are going to head back to in-person class. Just for your information, if you that means that we're going to turn in the paper homework starting next Monday. Okay, now last classes we talk about if we have a structure, we were interested in the stress at one point. Then first what we do is we use the equation that we know before, we're familiar with. We calculate the normal stress and shear stress. When that's calculated, then we can put those stress into the physical small cube, like the one that highlighted in red. With those information, now we can first start with the vertical plane and horizontal plane. We identify what are the stresses on the vertical plane and horizontal plane using the sign convention that we talk about. Again, just to review, the sign convention for normal stress is the stresses is pointing towards the center of the small cube. That is the positive normal stress. And if that stress is the normal stress is pointing away from the center of the cube, that is a tension. Sorry, let me start one back. It's a little bit early here, so let me start from the beginning. So if the normal stress is pointing towards the center of the small cube, that is compressions, and that is negative. And if the normal stress is pointing away from the small cube, that is going to be the tension stress, normal stress, and that is positive based on our sign convention. For the shear stress, if that shear stress is in a direction that is creating a clockwise moment, if you're taking the moment inside the center of the cube, that means your shear stress is positive. If that shear stress is counterclockwise, that means the shear stress is negative. With that sign convention, then we can reflect on these stresses on the vertical plane, horizontal plane. For example, for the vertical plane, your normal stress is pointing towards the center of the cube. Therefore, that is compression, and thus is negative. And for the shear stress on the vertical plane, since it's going from the bottom to the top, it's creating a counterclockwise moment, and therefore that is negative as well. Right? You can do the same thing for the horizontal plane. With that information, with the x-axis normal stress, y-axis normal stress, and shear stress identifying, we can use the equation to calculate what are the centers of the cube. And we can also identify what is the radius of the Mohr circle. And with those information, we can draw our Mohr circle. And with the Mohr circle, we can also identify easily what is the maximum normal stress, sigma 1, what is the maximum normal stress, sigma. And just keep in mind, each point along the beam has a Mohr circle to represent all the stresses on that particular point. And with the small physical cube, if you take that point of interest out, for that particular small cube, if you look at any of those different planes, there's the pair of stresses at that particular plane, it is 1 point on the Mohr circle. Using this as example, the vertical plane and horizontal plane, we can use the 2 points to represent those 2 points, stresses on those two planes. Okay. And the angle in the Moore circle is twice as that in the wheel stress situation. And use this again as an example. The angle between the horizontal plane and the vertical plane on the Moore circle is 180 degrees. And in the physical plane, that is going to be half of that in the Moore circle, which means we have 90 degrees on the physical plane. And that information is very useful because going back to the beginning, the goal here is to evaluate for this particular point on the structure, if we rotate a certain degree, we would like to know the stresses on that particular plane so that we can check to see if those stresses would create any damage on that particular structures, right? So with that said, for this particular small cube, if we rotate that alpha clockwise, after we rotated alpha clockwise, we're going to have our plane C and plane D. And the goal here is to find out the stresses on the plane C and plane D. What we can do is on the Moore circle, starting from the horizontal plane, we rotate that to alpha. After we rotate that to alpha, we're going to reach this plane D here. Because it's starting from the horizontal plane, rotate alpha, that is your plane D, right, in the physical plane. Similarly, on the vertical plane, if you rotate clockwise alpha, that is our plane C. So that is why on the Moore circle, start from the vertical plane. If you start from the vertical plane, rotate clockwise to alpha, that is going to be the plane C. Then our goal then is switch to find out the coordinates for the plane C and plane D, because that is representing the stresses on those two planes. And in the real world scenario, I also mentioned now, if you have any point of interest that is in direct contact with the external forces, like this point on top, that point right on top of the support, those points, we're going to have the horizontal normal stress, and also we're going to have the vertical normal stress. However, if you have any point in the middle which do not have direct contact with the loads, then your small cube, we're going to only have the horizontal normal stress, and we do not have any vertical normal stress. And today, later on in today's class, we're going to use an example to demonstrate how that works, because that is example that we're going to use to connect all the knowledge that you learned so far. Any questions so far? Are we good? Okay. Now, last class, we used an example. We used the small cube that we have identified the stresses before. We use that example to see if we rotate that small cube clockwise, 30 degrees. And how are we going to identify the stresses on the plane C and plane D? And then we're done with that. Now, the question comes, what if we start with the small cube that is already rotated certain degrees from the horizontal plane? And now what we would like to know is what are the stresses on the small cube that is in a position like what we saw at the beginning, right? Horizontal, vertical. How would that calculate that stresses? With that, I'll give you 2 minutes just to think about it. What would you do if you're given a problem like this? And we're going to look at this problem together. Again, I don't need you to calculate the answer. I just need you to think about, hey, if that is the case, what would you do? All right, that's our 2 minutes. Any thoughts on how are we going to calculate the stresses if we are giving a cube? That has already been rotated and we have all the stresses on it. How are we going to calculate the stresses for the small cube? That is at the original position. So one thing we can think about, right? We mentioned previously, for a Mohr circle, any point on the Mohr circle is representing the stresses on a particular plane. Now, if we have the stresses on this physical plane that being rotated, that means we have the stresses on this plane and that plane. And though each of those planes is going to give us a normal stress and shear stress, which is 1 point on the Mohr circle, right? So with that information, it is going to be the same as what we used before, using the stresses at the original position, because those are the 2 distinct point on the Mohr circle. We can use the exact same information just to put in the equation for the center and for the radius and use that information to draw the Mohr circle. All right, let me show you what I mean by that. Let me first share the screen of my iPad. Hold on. Let me connect this guy here first. Okay. Share the screen. Okay. All right, this is the question that we just looked at, right? We have a small cube, has been rotated 60 degrees clockwise from the original position. Now, what we can do here is we can first identify the stresses on 2 planes. For example, this is a plane B, and this is a plane A. All right, if we look at plane B, we have a normal stress is pointing towards the center of the small cube. That means that normal stress in compressions, right? With the compression, normal stress is going to be negative. So sigma A, that is -4. For the shear stress is creating a canonicalized moments here, and therefore that shear stress is going to be -2. So that is -2 tau. If we look at the stresses at plane A has a normal stress is pointing away from the small cube, which is 8 kilopascal. That means it is a tension stress, and therefore that is positive 8. That is our sigma 8. Okay. And with that, the shear stress, it is 4 kilopascal clockwise. Therefore, that is positive. All right, that is our tau there. And with that, yes, go ahead.
Why is the sigma for -4, -2? Why is it sigma A?
Oh, sorry, sigma B. Thank you very much. That is B, and this is A. That's right. Thank you.
Also, the tau for sigma A should be 2, correct?
That's right. This is 2. It's a little bit early here in New Zealand, so I'm just trying to wake up. Appreciate all the feedbacks on this. Okay. Are we good?
Yep.
All right, awesome. So with that said, we can substitute those stresses at 2 points into the equation that we used before. For example, the center, which is sigma A plus sigma B divided by 2 and 0. And that would be A plus -4 divided by 2 and 0. That would give us the center of the Mohr circle as 2 and 0. And the radius is sigma A minus sigma B divided by 2 square of that plus tau AB square root of that. If you put in the information, that's A minus -4 divided by 2 square plus 2 square, and that is equal to 6.3. Right. And with that said, with the center and radius, we'll be able to draw a Mohr circle easily. So the center is 2 and 0. We have the radius of 6.3, meaning that starting from the center, we go to the right 6.3. 1, 2, 3, 4, 5, 6. 6.3 is here. To the left, 1, 2, 3, 4, 5, 6. 6.3 is over there. 1, 2, 3, 4, 5, 6. 6.3 is somewhere here. 1, 2, 3, 4, 5, 6. 6.3 is somewhere here. Right. Those are the 4 points here. We can connect those 4 dots to create our Mohr circle. This is okay. Right. That is the Mohr circle. On this Mohr circle, those 2 points that on plane A and plane B can be represented by 2 points on the Mohr circle, right? So for plane A is 8 and 2. So 1, 2, 3, 4, 5, 6, 7, 8, 8 and 2. And that is our point 8 and 2. That is our plane A. Plane B is -4 and 2. 1, 2, 3, 4. 4 and 2. That is -4 and -2. That is the plane B. Now, if we connect those 2 points, it has to pass through the center, and it's going to be 180 degrees away from each other, because in a physical plane, those 2 planes are 90 degrees away from each other, right? Okay, now the question becomes, we need to find out the circle that is at its original position, right? We need to find out something like this. So getting from what we have right now back to the horizontal ones, what we need to do is, starting from plane A, if we rotate counterclockwise 60 degrees, that is going to be our horizontal plane, right? So if now we're starting at point A, if we go back 120 degrees, right? Because that is double than the angle in the physical plane. That is going to be our plane C. Okay, so that is somewhere here. If you rotate 120 degree, which is 60 times 2, right? So what we need to do is we would like to find out what is coordinates at this point and that point, because from the point plane A, if you rotate 120 degrees, this is going to be our horizontal plane. I think I was using blue for that one. Let's bring it back to, oops. Similarly, from plane B, if you rotate 120 degrees counterclockwise, this point here is going to be our vertical plane. What we need to do is to find out the coordinate for those two, right? Okay, so in order to find that, if you look at this, let me see, color. If you look at this triangle here, we know this is our R. If we know this angle here, then we'll be able to find out what is the Y, what is the X, and then we can find out the coordinates, right? But in order to find this angle, what we could do here is for 180 degrees, the whole line here, if we subtract 120 degrees here, if we subtract this angle beta here, that will give you the angle here. Let's say this is our alpha, right? So meaning our alpha is equal to 180 degrees minus 120 minus beta. The next question becomes, hey, how to calculate the beta, right? So for beta, we can look at this small triangle here. So we take this triangle out. We have, this is our R. This vertical line here is is 2, right? Because coordinate here is A and 2. So this guy here is 2. This distance here is A minus the center, which is 2. So we have 6 here. That means beta is equal to inverse tangent 2 over A minus 2, which is 6. That gives us 80.4 degrees. Now, the alpha can be calculated as 180 minus 120 minus 18.4. That would give us 41.6 degrees. Now, once that is identified, we can take a close look at these triangle here. For this particular triangle, we identified angle is 41.6 degrees. The R, which is 6.3. Now we were trying to find, hey, what is this Y and X, right? And we have done this many times. We can calculate our X is equal to R times cosine 41.6 degrees. That is 4.7. The Y is equal to R times sine 41.6 degrees. That is 4.2. Okay, with that said, we can identify the coordinates now. The coordinate of the horizontal plane can be calculated as center X minus X and Y. And that would be 2 minus 4.7, and the vertical coordinate is 4.2, and that would be negative 2.7 and 4.2. Similarly, for the vertical plane, we have center X plus X and Y, And that would be 2 plus 4.7 and negative 4.2. That means our coordinate is 6.7 and negative 4.2. Although there's questions on the chat, let me take a look. Inverse tangent. Julian, I don't understand your question there. If you can unmute and ask again, we can try to answer that.
Oh, I was just saying for finding beta, you use inverse tan.
Yeah, inverse tangent, right?
Yeah.
Okay. Did I say inverse tangent or did I say something else? I don't remember.
No, you said inverse tangent.
Okay. Since we have the vertical sine, we have the bottom side, right? That should be inverse tangent. Okay. All right. So that is the coordinates that we found for the horizontal plane and vertical plane. Now, if you look at this, if we have the y and x identifying the coordinate for the horizontal plane, right? That your y is your y that you identify, which is the 4.2. The x is going to be the x minus the 2, right? Because the center is 2. So now the x is 4.7, since we on a negative side, so negative 4.7 plus that 2, that will give you the negative 2.7, right? Therefore, that's negative 2.7 here. For the vertical plane, since this triangle and the triangle in blue, they are the same. So that means this is the y that we calculate, and that is the x that we calculate. That means the coordinate for this guy, vertical plane, we have the y as y, which is, sorry, in the negative side, so that's negative 4.2. The x is going to be the 4.7 that we found plus the center there. That's 2, right? So 4.7 plus 2, therefore that's 6.7. That's how we come up with that. With that said, now we can go back to our small cube. Let me go down so that we can look at the coordinates here. So if we look at the small cube at its original position, so we identify the horizontal plane. The coordinate is negative 2.7 and 4.2. Negative 2.7 means that we have compression normal stress, right? So therefore, that is a 2.7. Given the equilibrium, we have to have the 2.7 on top, pointing in the opposite direction. So that is our 2.7 there. For the shear stress is positive 4.2. That means it's creating clockwise moments. Therefore, that is the 4.2. Because the equilibrium at this point, the stress has to be 0. So that means the shear stress here is also 4.2, but it's pointing downward. On the other side, it's going to have the same magnitude shear stress, but in opposite directions, right? So that is shear stress. And if we look at the vertical plane, we have the normal stress as 6.7 positive. That means we have a stress is pointing away from the center of Q, that is the 6.7, and that is the 6.7. Okay. And that is how we are finding the small cube, the stresses on the small cube at its original position, even after you rotate the small cube in a certain degree and know the stresses on that particular small cube. All right. The procedure is the same. You just need to identify correctly what are the stresses on two planes that has a 90 degree each from each other and substitute in that equation. Then you'll be fine finding the stress there. All right, with that said, any questions on this? It's pretty straightforward, right? Yep.
Yeah,
Go ahead.
on a quiz or like exam, do you want us to finish our problem with drawing the stresses on the cube and their directions?
Yes.
Okay.
They're going to be, yes. Okay. All right. So with that said, that is our stresses problem. Now you know how to find the stresses on any of the plane rotate a certain degree if you know the stresses on this physical small cube, right? And the next example, what I would like to do is to help you connect all the knowledge that we learned so far. So we start from a simple supported beam with the loadings on it. Now, what I'm interested in is the point of interest highlighted in red. I would like to know the stresses on this particular point of interest, and also like you to draw the Moore circle on this particular at this particular point of interest, and find the angle of the principal stresses from the horizontal plane. Now I'll give you 10 minutes to give me a try, and then we're going to look at this together, okay? Now it's 11:35, so 11:45, we are going to look at this problem, the solution together. All right. Hope you get a chance to work this out, and given the interest of time, let's take a look at this together. Right, and this is our simple supported beam. We have 8 kips point loads at 1/3 of the beam, and we have another uniform distributed load 2 kip per foot on the last 1/3 of the beam. The point of interest is in the middle, and we can use the knowledge that we learned before to find out the reaction force. On the left side, 6.7 kips. On the right side, 9.3 kips pointing upward. Now, I'm not going to go through how we calculate those, but if you still have difficulty finding the reaction force, please let me know. We can sit down and work this out. With that information, we'll be able to draw our shear diagram and the moment diagram correctly. Now, with those identified, what we need to do is first identify what are the stresses at this point of ingress here, okay? Now, if we recall the 2 equation that we're going to use, right? Sigma is equal to negative my over I. Our tau is V times Q divided by I times B, right? So in order to calculate those stresses at a point of ingress, what we need is first the moment of inertia for the cross sections. We also need to calculate the first moment of area Q, right? The moments at the point of interest, we can identify that as 24.2. The shear at the point of interest is negative 1.3. So those information we can extract from the shear and moment diagram without any problems. So in order to calculate the moment of inertia, again, the moment of inertia is the property of cross sections, right? It won't change no matter where your point of interest is located. The I is equal to 112 BH cubed. That is 112. The B is 1. The H is 2 to the third. That would give us 0.667 feet to the fourth. Right. That is a moment of inertia. And in order to find out the tau, we do need to have the first moment of area. To calculate the first moment of area, we first shade the area either above or below the point of interest. I'm going to take the one above. It doesn't create any different for this particular case since it is a rectangular cross section. Now the Q is going to be equal to A times D, right? A is area for the shaded area, that's easy, that's 1, times 0.5. And the D is the distance between the centroid of the shaded area, which is in the middle of the shaded area, to the overall centroid of the cross section, right? And that is our D. We have this distance here as 0.5. The distance between the centroid of shaded area to 0.5 is 0.25, right? Half of that. So if you add those up, that is going to be 0.75. So that is 0.75. If you calculate that right, our Q is going to be equal to 0.375 to the third. Now with all the information calculated, now we can easily calculate what is the normal stress. Sigma is equal to negative my over I, that's negative. M is 24.2 kip feet. Y is the distance between the point of interest to the centroid, right? Is that right? Anyone still with me, or is 11? All right, 11:50 your time, right? Should not be that sleepy. So the Y is distance between the point of interest to the overall centroid, right? That is the D, that is the Y, which is 0.5. So that is 0.5, substitute in the equation, divided by I, which is 0.667. That would give us a sigma is equal to negative 18.15 KSF. Now the tau is equal to V times Q divided by I times B. The V is negative 1.3. The Q is 0.375 as we calculated. And I is 0.667. And the B is the width, right? That is 1 foot. So if you calculate that out, that's negative 0.731 KSF. All right, with the stresses calculated, let's look back a little bit on this beam, right? If we take these beams out, cut it. So this is our beam, right? We have the 6.7 in here, and we have the 8 cubes in there. And we calculate, from the shear diagram, right? We know this shear is 1.7, 1.3 is negative, therefore it's pointing outward. We know the moment, that is 24.2 feet, right? That is from our shear moment diagrams. Now, this point of interest, it is this small cube, which is 0.5 feet from the top, right? This is our point of interest. If we take this small cube out, take small cube out, we just found our shear stress as negative 0.731. It's negative, that means it is categorized, right? So that is 0.731 KSF. The normal stress is negative 18.15. That means it's pointing toward our center of the cube. So that's 18.15. Okay. Because of equilibrium, the other side is going to look like this. 18.15 KSF. Right, and we need this point, the shear, to be 0. Therefore, the shear has to go this way and has to go to that way at the bottom. And are we going to have the vertical normal stress for this one?
No.
Nope. Why not, CC?
There's no like direct point load or concentrated load acting like that.
Excellent. Because the point of interest here is not in direct contact with any external load. Therefore, we will not have any vertical components of the normal stress. Right, excellent. So with that said, this is the small cube for that particular point. Now, this is going to be back to what we already practiced many times, right? With the small cube, giving all the normal stress and shear stress, how to find the Mohr circle, right? So what we first do is we identify the vertical plane. We identify the horizontal plane. For the vertical plane, we have the sigma x, we have the tau. The sigma x is negative 18.15. The tau is negative 0.731. And if we look at the horizontal plane, the normal stress is 0. The shear stress is hot rise, therefore it's positive. So that's positive 731. This is sigma y, this is tau, right? Now with that information, we can easily calculate the centers and we can calculate the radius, right? Their center is sigma x plus sigma y divided by 2 and 0. Sigma x is negative 18.15, sigma y is 0 divided by 2. That gives us the center at negative 9.08 and 0. And the radius is sigma x minus sigma y divided by 2 squared plus tau xy squared, square root of that. You put in the number, that's negative 9.08 squared plus 0.731 square root of that, that would give you 9.11. Okay, now your sigma 1, the maximum normal stress, is just center x plus r, that is negative 9.08 plus 9.11, that is 0.03. Sigma 3 is center x minus r, that's negative 9.08 minus 9.11, that would give us negative 18.19. Okay, and that is the sigma 1, the maximum normal stress and maximum shear stress. Now, with that information, we can start to draw our Mohr circle. So this is going to be, let's see, 18.1. Okay. So to draw the Mohr circle, we have the centers at negative 9.08, right? So let me see. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Okay, we have the x coordinate as sigma, y coordinate as tau. The center is located at negative 9.08 and 0. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 9.08 and 0. That is the center. From the center, we count left 9.11 and count right 9.11. So we're going to have the sigma 1 here. That is our sigma 3 over there. And this is the maximum shear stress point. And this is our maximum, minimum shear stress point. If we connect all those, that is going to be our Mohr circle. Okay. Now with this Mohr circle, we the 2 points that we're identifying, this one here is our 0.731, and that is the point for the horizontal plane. And we also have a point there, which is negative 18.15, negative 0.731, and that is the vertical plane. Connect that to the centers. That should be 180 degrees away from each other. So now the second question that in the statement is asking, hey, what is the angle between the horizontal plane and the principal stresses plane, right? The principal stress plane is sigma 1, sigma 3 there. the horizontal plane is this, that basically as asking, hey, what is this angle here? To find that angle is relatively easily. So if you look at this triangle here, I'm going enlarging it here so that we can take a look at that. Oops, that is not a right angle here. So horizontal. All right, if you look at that, this distance here is 0.731. And that distance is going to be the R, right? It's the center of the circle, which is 9.08. Therefore, in order to calculate this angle here, let's say this is our beta. The beta is equal to inverse tangent 0.731 minus 9.08. And that will give you the beta is equal to 4.6 degrees. And this is the angle in the Morse circle, right? 4.6 degrees. In the physical plane, the angle is going to be 4.6 degrees divided by 2, which is 2.3 degrees, right? On that particular small cube there, we only have our principal normal stress, right? That is negative 0.03. Equilibrium, that is 0.03. On that particular plane, we have the minimum principal stresses, which is negative 18.19. Therefore, that is negative 18.19. Right, that is the small cube there. We did not ask you to draw the small cube on the problem statement. We're just asking for the angle. But I'm just trying to draw that for you so that you know what are those stresses on the small cube as well. Okay, now with that said, that is the example that I would like to use to help you connect all the knowledge from the beginning, right? Giving a beam how to find the reaction force, how to draw a shear moment diagram. After you draw the shear moment diagram, how to identify the stresses at the point of interest, and draw that small cube with the stresses of at the point of interest. And from there, calculate what is the center and what is the radius for the Morse circle. Draw the Morse circle, and with the Morse circle is drawn, then now we can try to identify stresses at any plane if you want to rotate that in certain degree to evaluate if that is just the limit. Okay. With that said, that's basically what I would like to cover for today's lectures. And your homework is going to be online. Just a friendly reminder, on this Wednesday's class, we're still going to be have that as a centralized Zoom section. But next Monday, we are going to be back in on campus to do the in-person class. With that said, if you have any question, I'll be here to answer your question. If not, then I'll see you on Wednesday, and I'm going to share the recording on Canvas and post the homework online. All right, thanks everyone.
It looks like there was a chat question.
There is a question about are we going to have a quiz this week? So we won't have quiz this week. So we will have a quiz next Wednesday instead. All right, thank you everyone. Go ahead.
I have a question. Can you go back to where you have the 6.7 moment for the AY and then the 8 kip going down? Where's the 1.3 come from? The tau 1.3.
Are we talking about this?
No, the problem we're just working on.
Okay. This guy?
Yes. Let's see, go down a little bit. Right there, the 1.3. and we have the 24.2 kips per foot.
Oh, okay. So if you look at this, right, this is 1.3, right? The shear,
Oh, okay.
and the moment is
Oh, so it's that point.
24.2, right? It's directly from the shear moment diagram.
Oh, okay.
Make sense?
Yes, yes. Thank you.
All right. Sounds good. I'll see you on Wednesday.
See you Wednesday.
All right. Bye-bye, everyone.